So hello students, it's nice to see you after a long time. The first lecture that we are going to have today is going to be on the heat conduction equation and its simplifications. So before that, let's recall what we did in the previous classes. So we studied about heat conduction. We said that heat conduction is a mechanism either due to electron clouds, as it happens in metals like in electrical conductivity, or is it because of lattice vibrations. So we said that the thermal conductivity, which is basically the property of the material, which when it is high, the heat conduction through the material is high for a given temperature difference and thickness, and is low. When it is low, then the heat conduction is also low for a given material thickness and temperature difference. So we said that perfect crystal diamond has the highest known thermal conductivity out of naturally occurring materials, and its conductivity is about 2000 watts per meter Kelvin. The units are watts per meter Kelvin. That's something that we had derived. And then we said that metals are very good conductors. So we get conductivities from a few tens to a few hundreds. Silver and gold have high conductivities of the order of 300, 400. Copper has a high conductivity, about 400. And so on. We had looked at those values last time. We also said that insulation is another good property, and we were looking at materials that are good insulators, that have a low conductivity and therefore can prevent heat losses from happening from a given material. So we also looked at the Fourier law of heat conduction. Let me switch to a screen where I can write and show you, so it can be interactive. The Fourier law of heat conduction was shown like this in the last class. Q dot, which is the rate of heat flow, is equal to minus K A into del T by del N, where K is the thermal conductivity, we just discussed about it. A is the area through which the heat is flowing, and del T by del N is the temperature gradient in the direction normal to A. So the heat flux, the heat flow, the Q dot here given is in the direction N, which is perpendicular to the area A. So that is the expression that we have. So the heat conduction equation is going to use the Fourier conduction law as well as the first law of thermodynamics. So let us look at how that is done. So in order to derive the heat conduction equation, we need to first define what is the object on which the heat conduction equation is going to be derived. So that is done by saying, okay, let's this be an arbitrary solid inside which heat conduction is happening, inside which let us define a small elemental control volume of the shape of a cuboid, okay, and let the coordinate directions be x, y, and z. So this is x, this is y, and this is z. So the coordinate directions for this are x, y, and z. Now this cuboid can be taken out and enlarged in size so that we can write the heat conduction equation for it. So let's draw that on a slightly larger scale here. So this is your elemental cuboid that we have drawn there. Okay, so let's also draw the hidden surfaces there. So let us say this is the cuboid whose length in the x direction is delta x, in the y direction is delta y, and in the z direction is delta z. This is the size. So the volume of the cuboid is delta x, delta y, delta z, and the areas perpendicular to the x direction, which is this, would be delta y, delta z. The area perpendicular to the y direction, which is this, would be delta x, delta z, and the area that is perpendicular to the z direction, which would be this heat flux on this side and this side, let us say, that would be delta x, delta y. Okay. So if I write the first law for this control volume as du by dt, we are writing it in the rate form. Du by dt is q dot in plus w dot on. This is the first law. Now the q dot in is the term that is going to be associated with the heat transfers that are going to be coming in from all the faces, but the w dot on is going to be absent in this case because it's a solid material. There is no movement, there is nothing that is coming in, and we've also written the first law for a closed system because there is no inflow or outflow that is going to happen because it's all solid. Now since it's a solid and there is not going to be any deformation that is going to contribute to the heat transfer in this case, the w dot on term will also be neglected, and this q dot in will need to be expanded as summation of q dot j, where the j is surface number. So here in this particular example we have a cuboid, so you have 6 faces, so j is equal to 1 to 6. So that is your heat summation that you'll have. And what is the 6 flux terms that you would have? Suppose I call this as q dot double prime x, which is the heat flux in the x direction, and q dot double prime x plus delta x, which is the heat flux in the x direction, but on the other face at x plus delta x. If this location, this corner is the origin of this block is x, then this is x plus delta x. Similarly, if the front face is z, the rear face is z plus delta z. If the bottom face is y, the top face top face is y plus delta y. So this would be q dot double prime y, and this would be q dot double prime y plus delta y, and similarly this would be q dot double prime z, and this would be q dot double prime z plus delta z. Now these q dot double primes, the double primes actually denote that it is per unit area. So if you want to calculate the total heat flow coming from, for example, this face, which is the left face of the control volume, then that will be equal to the q dot x double prime multiplied by the area of this face, which will be equal to delta y delta z. Right? So that is the way we write it. So if I do that for every face, then the right hand side, which is the summation of q dot I, would start looking like this. So it will be q dot x double prime minus q dot x plus delta x double prime, the whole thing multiplied by delta y delta z, plus q dot y double prime minus q dot y plus delta y double prime multiplied by delta z delta x, plus q dot z double prime minus q dot z plus delta z double prime, whole thing multiplied by delta x delta y. This is going to be the right hand side of this equation while looking at only the heat fluxes. Suppose this solid is generating heat within itself. How can that happen physically? For example, if I have a heat conductor, an electrical conductor, which has ohmic heating that is happening inside it because of electrical resistivity, then at every point inside the solid, there will be some amount of heat that is produced from within because of dissipation of electricity into heat. So that in terms of heat transfer can be considered as a source or a generation of heat. So if that happens, suppose there is a uniform volumetric heat generation of Q dot triple prime in this whole volume, then the total heat generated in the volume would be this multiplied by delta x, delta y, delta z, and this would also get added to the right hand side in order to quantify the total amount of heat added by heat inflow through all the surfaces plus the heat generated within it. And what would this be equal to? This would be equal to the left hand side, which is d by dt or del by del t. Let me erase this and write it again. Yeah, so that is del by del t of, what is that capital U? The capital U is nothing but the mass multiplied by the specific internal energy, which can also be written as mass multiplied by the specific heat at constant volume multiplied by temperature. For solids, it's the same CV or CP, so you can just write it that way. So then you can actually use this here. This will be equal to mCVT. So this is the next form of the equation that we just started with. So the left hand side looks like this, del by del T of mCVT, and that is equal to all of these terms now. So there are two heat flux terms here, two heat flux terms here, and two heat flux terms here, and there is a heat generation term which is here. In order to show that it is generation, let us write Q dot gen triple prime. Okay. Now how do we go about simplifying this? We'll use the Fourier conduction equation. The Fourier conduction equation says that Q dot x double prime, which is the heat flux, that is Q dot by A in x direction at x, will be equal to minus K del T by del x at x. Similarly, Q dot double prime x plus delta x will be equal to minus K, and this can also be said that K at x and K at x plus delta x if we want to also consider spatial variation in thermal conductivity. Otherwise, it can be just written as K if it is a constant. So now this is K x plus delta x multiplied by del T by del x at x plus delta x. So now the first term, which is nothing but this minus this, okay, this minus this, would actually be this term minus this term, right? So when I do that, the first term will retain the negative sign, but the second term, because it is subtracted, minus of minus would become plus, and the first term would be this minus this, the first term minus the second term multiplied by delta y delta z. That is the area term. So what we'll get is we'll get delta y delta z multiplied by kx plus delta x, because that is positive, we'll write that first, into del T by del x at x plus delta x minus K del T by del x, kx del T by del x at x. Okay, so that is your first term. Similarly, you will have the second term, which is delta x delta y multiplied by rather delta z delta y delta z delta y multiplied by ky plus delta y multiplied by del T by del y at y plus delta y minus ky del T by del y at y. So that's the second term, plus delta x delta y multiplied by, what will be the first term there? Kz plus delta z, sorry, Kz plus delta z multiplied by del T by del z at z plus delta z minus Kz del T by del z at z. Okay, this plus Q dot triple prime into delta x, delta y, delta z will be equal to del by del T of this mass. We can also write it as rho into volume, density into volume. That will be rho times delta x, delta y, delta z multiplied by CVT. Right? So this is the next form of the equation. Now in this we see that there is a term which is at x plus delta x and the same term at x. Similarly, a term at y plus delta y, the same term at y. There is a term at z plus delta z, the same term at z. These are subtracted and they are multiplied by this. Now if I divide this whole equation by the volume, which is delta x, delta y, delta z, what will happen? There is a delta y, delta z here, which gets divided with this delta x, delta y, delta z. I'll get a 1 by delta x there. Similarly, there is a delta z, delta y here. If I divide it, okay, so this will be delta x, delta z. Right. So if I divide this term by delta x, delta y, delta z, I get a 1 by delta y, and similarly if I divide this by delta x, delta y, delta z, I get a 1 by delta z. So I'll have a 1 by delta x multiplied by this bracketed term, which is the difference between this quantity at x plus delta x and this quantity at x. Similarly, this will be divided by delta y of a quantity which is at y plus delta y and the same quantity at y, and this will be 1 by delta z of a quantity at z plus delta z and the same quantity at z. So when I divide this whole equation by delta x, delta y, delta z and take limits as the delta x, delta y and delta z tend to 0, I get a differential form of this equation, which will say del by del x of kx del t by del x, okay, plus del by del y of ky del t by del y plus del by del z of kz del t by del z. Okay, these are the three terms that we have, plus this q dot triple prime generation will stay as it is because the delta x, delta y, delta z would have got cancelled, and this would be equal to del by del t of rho CVT. So this becomes your heat conduction equation. Now kx, ky and kz are conductivities in the x, y and z directions respectively. If the material is isotropic, then the conductivity is uniform in all directions. For example, materials like metals, which have the same properties in all directions, the delta x, delta y, delta z will be, kx, ky, kz will be equal. Whereas if you have a material which is a laminate, for example, like plywood, or even wood for that matter, which has strands in one direction but layered over the other, then the conductivity along the strands and the conductivity perpendicular to the strands would be different. Similarly, in the plywood, the conductivity along the layers of the lamina and the conductivity across the layers would be different. So in that case, the conductivity itself actually becomes a tensor quantity. Otherwise, in the most simple case, we can actually say kx equal to ky equal to kz equal to k for isotropic materials. So in this course, we'll deal only with isotropic materials. So we'll talk about kx equal to ky equal to kz equal to k, and therefore this whole equation would get simplified to something like this: del by del t of rho CVT is equal to del by del x of k del t by del x plus del by del y of k del t by del y plus del by del z of k del t by del z plus q dot triple prime elevation. Now this equation is what we call as the heat conduction equation. Okay, so basically what have we done? We have basically applied the first law for a closed system to an elemental control volume or an elemental volume of delta x, delta y, delta z within a medium that is conducting heat, and we have tried to simplify it using the Fourier conduction law in order to arrive at an equation. So now this is a differential equation of temperature in x, y, z and t, and there are parameters which are properties of the material. One is the conductivity, the other is density and specific heat. These three are properties of a given material. So this is the most generic form of the heat conduction equation, with the assumption that the material is isotropic, right? Now this is a complex equation, and if k is a function of x, y, z and t, then it becomes a nonlinear equation as well. Okay. Now in the very first course, let's not get into very complex systems, but we can simplify this into much simpler forms for the simplest understanding, the first understanding of the conduction heat transfer. So let us try to do that. What are the simplifications that would be feasible here? One simplification that will be feasible is that the left hand side is equal to 0, that is, there is no time variation of anything. So we have what is called the steady state. Which is del by del t of rho Cv t equal to 0, which is also equal to the right hand side. This is one simplification. When does this happen? This is a physical situation that happens whenever the variation with time of the temperature in any substance stops happening. When does that start? When does that happen? For example, let's take the wall of a classroom. The wall of a classroom, the inside of it is maintained, let us say, using an air conditioner at about 25 degrees Celsius, and the outside of it is at ambient temperature. Let us say through the period of the day, the ambient temperature stays not very different from, let us say, 25, 26 degrees Celsius on a particular day, or maybe let us say 30 degrees Celsius on a particular day. So then you have air at about 30 degrees Celsius on the outside and air at about 25 degrees Celsius on the inside, prevailing over a long duration of time. And during this period of time, the whole wall attains a temperature inside it such that there is no change in temperature with time after a certain period of time. Right? So this is a steady state condition. So a steady state condition can be achieved when a certain set of boundary conditions are maintained in a particular system for long durations of time, that the transients or the time dependent variations of temperature stop and eventually the temperatures go to steady state. So this is one assumption. The other assumption is constant properties. So if I don't invoke the steady state assumption but only the constant properties assumption, then from the first equation, from the first left hand side of the equation, which is this one, the rho Cv would come out of the differential, and from the entire right hand side, the k would come out. So I can group the k and rho Cv together as a single variable. Okay, so you have k divided by rho Cv is one property of the material which we call as alpha, the thermal diffusivity. Why we call it thermal diffusivity, we'll come to a little bit later when we look at the analogy between mass diffusion and heat conduction. But at this stage, let us just call it thermal diffusivity. So this is basically a composite property, k by rho Cv, and if you put the respective units, So K is watts per meter Kelvin, rho is kg per meter cube, and CV is joules per kg Kelvin. If you put them and simplify, this will have a units of meter square per second. This is basically what you will get when you put these things. So if I use this alpha, then this equation, but at constant properties, will look something like this. It will become del T by del T into 1 by alpha would be equal to del squared T by del x squared plus del squared T by del y squared plus del squared T by del z squared plus q dot triple prime generation divided by K. Right? So this is one simplification of the equation that can be done. So you can already see this equation looks a lot more compact than, for example, this one, right? That is because we have taken the properties to be constant. Now on this, if I look at the steady state assumption, then again this term will disappear. So you will get a Poisson equation, to be pronouncing it correctly. So it's del square T by del x square plus del square T by del y square plus del square T by del z square would be equal to a constant, which is q dot triple prime gen by K. So that's a three-dimensional heat conduction equation with heat generation at steady state. So that is a second simplification that one can look at. A third possible simplification of the heat conduction equation arises out of reducing the dimensionality of the equation. The present equation is three-dimensional and transient. Reducing its dimensionality would basically involve chopping down one of the coordinate directions or two of the coordinate directions in order to make it two-dimensional or one-dimensional. Let's understand when this can happen. So reduced dimensionality is the third possible simplification. Look at a wall, for example, between two rooms. So the wall would have a finite thickness, but would be large in extent in both this direction, y direction, and in the z direction. This direction is also very large, and this direction is also very large. The wall in its length and breadth would be very large, but its thickness would be a much smaller direction or much smaller dimension as compared to the other two. So for example, the Lx, which is the x length of the thing, if this is the x coordinate, the x length of this wall is much less than its Ly and Lz. So this is a case where if you look at the wall between two rooms, the variation in temperature along this direction as well as along this direction would be much smaller as compared to the variation across the thickness. Right? For example, if a classroom is maintained at 25 degrees Celsius and outdoor is maintained at 30 degrees Celsius, then this entire wall, for example, which is of the classroom, would be facing 25 degrees Celsius. So along the length and breadth of the wall, the variation in temperature would be very small. And in the same way, the other side of the wall, which is exposed to the surroundings, along the length and breadth of the wall, it will be exposed to the same ambient, and therefore the thickness of the wall is the direction in which the maximum temperature change occurs, and therefore the temperature gradients are the biggest there. So if you go back to the equations that you looked at, the gradients in y direction and z direction would become extremely small as compared to the gradients in x direction, that out of these three terms that are here, the second term and the third term can be dropped as negligible as compared to the first term. So then it becomes what we call as a one-dimensional problem. So the geometry itself is not one-dimensional. The geometry, as you can see, is a three-dimensional geometry, but the variation in two of the directions, the y and the z directions, is small as compared to the variation in the x direction, and therefore you can neglect the gradients in the y and z directions in comparison with x direction. So then it becomes a one-dimensional problem. Another example is when you can reduce it to a two-dimensional problem. Let us take a bar, let us say of a square or rectangular cross section of a very large length. Okay. Now, if this bar is exposed to a certain environment, say for example like a steel bar which is getting heat treated in a furnace, then the furnace would, the surfaces of the bar would be exposed to the furnace temperature, and the interior of the bar may have been at the initial temperature which was ambient. So the gradients across this thickness and across this direction would be very large as compared to the gradients along this direction at any location. So then if I call this as x and y directions and this as the z direction, the gradients in the z direction are negligible as compared to the gradients in x and y directions. Then it becomes a two-dimensional problem. Right? So when these are done, then the terms from the original governing equation drop out and you get simplified equations. So let us try to see some of them. So if I have constant properties, which means K, rho, Cv are constant. Constant meaning they don't vary with x, y, z or t, or for that matter they don't vary with the temperature. Right? Then you would have the governing equation that was written in this page. In this governing equation, let's also assume that the transient term and the term concerning the heat generation per unit volume are both absent for simplicity's sake. Then we would have the governing equation with only these three terms. They are simplified to now that extent. So you would have del squared t by del x squared, del t squared t by del y squared, and del squared t by del z squared terms. Now if I consider a problem which is one-dimensional, then these two terms also drop out and I'll have only this term remaining. And if I have a two-dimensional problem, then it's this term that drops out and I'll have these two terms remaining. So if I go back and start writing those equations, so I get the one-dimensional conduction equation. So I also add the assumptions steady state and q dot triple prime gen are 0. These are the assumptions that we make. Then the one-dimensional equation simply becomes d squared t by dx squared is equal to 0, because that is the only term that remains. And a two-dimensional equation would become d squared t by dx squared plus d squared t by dy squared equal to 0, which are both the classical Laplace equations in 1 and 2 dimensions respectively. The three-dimensional case would be a three-dimensional Laplace equation. So that's the equations that we come to. So now let us try to focus on solving this equation analytically. So what are we trying to do now? We are trying to look at a simple one-dimensional wall. So it's infinite extent in this direction as well as in the depth-wise direction. So you have, this is x equal to 0 and this is, let's say, x is equal to L. Now these two walls, this left surface and the right surface, are maintained, let us say, at temperatures T1 and T2 respectively. And we would like to solve this equation and find out what the temperature distribution in this wall would look like at steady state. So you start with the steady state governing equation, d squared t by dx square equal to 0. So if I integrate this twice, I will get, first the integration will yield dt by dx is a constant. So let us say that is c1, and t equal to c1x plus c2. Now there are two boundary conditions, x is equal to 0, t equal to t1, and x is equal to L, t equal to t2. So if I use this boundary condition, I get from this equation t1 equal to c2. And from this and this together, I would get t2 is c1L plus t1. Right? So if I put these two back into this equation, then I'll get the solution for the equation that I tried to set out to solve with these boundary conditions. So what does that look like? It looks like t is equal to t2 minus t1 divided by L into x plus t1. Now this solution can be rearranged to write t minus t1 by t2 minus t1 is equal to x by L. Right? So this is the solution that we can get. So the solution basically means that it's a straight line between these two. It's a linear equation. So it's a straight line between these two. The temperature is T1 at this end and T2 at this end, and in between it's a straight line between T1 and T2 whose slope is x by L. So that is the solution that you get. Now using this, so the solution that basically comes out here is that if you have a steady state one-dimensional constant property system, the temperature distribution does not depend on the thermal conductivity or any other property of this, because the governing equation itself is devoid of the properties. So whether it's a brick wall or a steel wall or a wall made of any other homogeneous material like concrete is not a homogeneous material, let us say any metallic wall or a steel wall or a uniform masonry work wall, whatever wall that is, so long as the thermal conductivity, density and specific heat are constant and uniform throughout the region, and the problem is one-dimensional, the solution would always be this. So the steady state solution is not different for materials with, for example, different conductivities or different densities or different specific heats. That is one fact that you get. The second thing that you get is that if I try to find out the heat flux at any location, which is q dot by A, which is given as minus k into del T by del X. In this particular case, it's dt by dx, because it's a total differential equation. This would give, from your previous slide, you know that dt by dx is a constant C1, and that C1 is equal to T2 minus T1 divided by L. So if I use that expression here, it will be actually minus k times T2 minus T1 by L, right? So this is your heat flux at any location, and this is independent of x. So this is quite interesting, that the heat flux any location is independent of x, which is understandable because we are looking at a problem of steady state. So there is no accumulation of energy at any layer in the wall, and therefore the heat flux entering the wall is the same as the heat flux leaving the wall, and that is why this is there. So now this is equal to, now the negative sign can be absorbed here and you can write it as T1 minus T2 by L into K. Now if I write for Q dot, which is the total heat transfer through the wall, which will be equal to Ka by L multiplied by T1 minus T2, or this can be written as T1 minus T2 divided by L by Ka. Now this equation is called the electrical analogy of heat transfer, where this term Q dot is akin to the current and the temperature difference is akin to the potential difference, and this term is what we call as the thermal resistance RTH due to conduction of the wall. So the thermal resistance of a wall is written in the form of L by Ka, where L is the thickness of the wall and K and A are the thermal conductivity and surface area of the wall respectively. This electrical resistance analogy can be further extended for other classes of problem as well. So suppose this is the wall, with this wall at this side of the wall at T1, and let's say this side of the wall is at T2, and you have the ambient temperature which is T infinity, which is lower than that. So the temperature profile would typically look something like this. This is a straight line because of steady state conduction there, and after that it will go tapering off like that because of the way the convective heat transfer operates. We will discuss about that a little later as how convection operates. But between T infinity and T1, which are the two temperatures across which this heat transfer is happening, if this heat transfer is at steady state, then everywhere it is Q dot. Then this Q dot can be written as T1 minus T2 divided by L by Ka. This is something that we have seen, but which will also be equal to the heat transfer on this side, which is usually written using the convective heat transfer coefficient of Ha into T2 minus T infinity. Now if I write the second term also in terms of thermal resistance, then it can be written in the form of T2 minus T infinity divided by 1 over Ha. Okay. So now this 1 over Ha becomes the thermal resistance due to convection on the outer surface of the wall. So if I now combine these two, we can write the Q dot, okay, multiplied by the respective resistances. So L by Ka plus 1 by Ha can be written as, so what is Q dot into L by Ka? According to this, it should be equal to T1 minus T2, and Q dot into 1 by Ha is T2 minus T infinity, so plus T2 minus T infinity. So the T2 gets cancelled out, so you get T1 minus T infinity. So what can we write? T1 minus T infinity divided by the sum of the two resistances that is here is the same as Q dot. So it again comes into the same electrical analogy. So you get Q dot is equal to T1 minus T infinity divided by L by Ka plus 1 by Ha. This becomes a very powerful analogy. So if you go back here, we can look at this one as one electrical resistance and this convection as another electrical resistance. So if there is T1 here and T infinity here, with this as L by Ka and this as 1 by Ha, then the Q dot, which is going through this, is written as T1 minus T infinity divided by the sum of these two by electrical analogy. So this is basically what we do. This can further be extended also. Suppose I have a multi-layered wall. So let us say this kind of wall is commonly encountered, for example, in furnaces, where suppose this is the highest temperature, let's say Tg, where the gases are there, and from the gases there is a certain temperature gradient to the inner surface of the wall, and after that there is the refractory wall, the brick wall that is inside, and then on the outside of it there might be air gaps, there might be various commercial insulations, and there may be a metal cladding that's on the outside. So there are multiple layers, each one having a conductivity, let us say K1, K2, K3, K4, and each one having a thickness L1, L2, L3, L4, and all of them have the same common area A. Then the total resistance offered by this composite wall can be written as L1 by K1A plus L2 by K2A plus L3 by K3A plus L4 by K4A, and this whole thing, when it is used to divide, so 1 over this, or T so if this surface is at T1 and this surface is at, let us say, T2, then T1 minus T2 divided by this resistance would be actually equal to the Q dot that goes through this. And if I consider the convection on the inside and the convection on the outside also, I would have a term of 1 over H1A on this side and another one plus 1 over H2A on this side, and all of them put together will give me the total resistance. And if any one resistance is increased or decreased, accordingly the heat losses that go through the wall will decrease. So the design of the furnace wall insulation can be done using this electrical analogy very simply. So we'll solve tutorial problems on this so that it becomes clear. So this is what we call as the electrical analogy, which is a direct fallout of the one-dimensional solution of the heat transfer through a constant property wall at steady state. Okay. So this electrical analogy should only be used, strictly speaking, at steady state and should not be used in any other condition. Particularly in transients, for example, the electrical analogy should be avoided because the equation doesn't fall in that form for other kinds of solutions. But only for steady state solution we can use the we can use the electrical analogy. Okay, so we'll stop here and try to understand whatever we have done. I would upload some material for you to look through from textbooks on your Moodle page directly. It will not be on your cloud page which you are accessing right now for the video material, but I will upload the handouts on your Moodle which you can access only from your Kerberos login, and therefore it doesn't go out of the IIT servers into the cloud because they are copyrighted material. I would like to give you a chapter of one of the books which you can read from there. Okay, so we'll stop here and continue in the next lecture.